So I'm Zolotov. I'm a postdoc at Hebrew University. And today I'm going to be talking about how to form compact star-forming spheroids. And the work I'm going to be talking about has been done in close collaboration with several people. And I want to point out in particular Daniel Savarino, Avishai Deckel, and Dylan Tweed. And all of the results that I'm going to be showing are from a suite of simulations using HydroArt. And what's really special about these cosmological zoom-in simulations is that it's a really large sample for high-resolution simulation. So we have about 30 relatively massive galaxies that have been run all to redshift 2, but some even down to redshift 1. You can see it doesn't span a large range in halo mass, but you can see that they're about 1 × 10⁻² at CF2. And their resolution is about 20 to 50 parsecs. So as I was saying, these are extremely high resolution cosmological simulations. And I'll be showing 2 versions of these simulations, one which we're calling Generation 1, which just has thermal feedback, and then Generation 3, which has radiative pressure implemented. And Daniel Savarino is going to be talking about the radiative pressure implementation this afternoon. So let me motivate my talk a little bit by talking about the recent observations. So this is from the Candles collaboration in a paper led by Burrow et al. And what you see here at high redshift are these very compact and star-forming galaxies. So these have been termed the blue nuggets. And as you go down to lower and lower redshifts, and then eventually to redshift 1, what you find is that there's very few of these compact star-forming galaxies, but a lot of these very compact and red quiescent galaxies, these red nuggets. And so this leads to at least 3 interesting open questions. The first is, what makes these galaxies compact at high redshift? The next is, what quenches these galaxies as you go down to lower redshifts? And finally, what's the evolutionary path here? So do these galaxies quench and shrink, or do they shrink and quench? So because we're talking about the central regions of these galaxies, obviously a natural connection is bulge formation. So this is something that Dylan talked about in his talk earlier in the week, but I want to show our results again. So what we did is at every snapshot for every simulation, we define a kinematic bulge, and then we ask, where did the stars in the bulge form? So if the stars in the bulge formed in situ in the bulge, you see them in blue. If they formed in the disk and then migrated inwards, you see them in green. And then if they formed in a secondary galaxy and were then accreted onto the bulge, you see them in these 2 different shades of red. And as I was saying, this is a relatively large sample of galaxies. We have about 30 simulations. So these are the averages of the stacks. And what you see, which is quite interesting, is that at high redshift, something like 60% of the stars in bulges formed in situ in the bulge. And then this fraction decreases down to about 30% by redshift 1. But you see that there's also a significant fraction of disk stars, so stars that formed in the disk and then end up migrating inwards to the kinematic bulge. So since you have all of this in situ star formation in the bulge, you clearly need some gas fuel to make these stars. And you have 2 options for bringing in this fuel. The first is to have a wet merger, which brings in a lot of gas to the primary galaxy. And the second is disk instability. And one of the things that we see in these simulations is that the disks tend to go through periods where they're incredibly unstable. And that's what you see here in this time sequence, is this disk galaxy, which has a lot of clumps, which is the signature of this disk instability phase. And this unstable phase not only brings in clumps to the center of the galaxy, but it also brings in stars and gas. So Avishai talked a lot about this on Tuesday and gave us a nice treatment of it, so I won't go into it in much detail, but this instability parameter is really driven by the high surface density of gas at high redshift because of the high accretion rates and high Z. And so you have this very unstable phase. The torques between the perturbations drive angular momentum out. They've let the mass flow in. And what we find on average is that the inflow rate of gas is about 25 solar masses per year at redshift 2. And of course, there's been a lot of observations that there are indeed very clumpy and turbulent disks at high redshift. So let's see what the simulation showed. This is the same parameter space as the Burrow et al. Paper, where you're looking at the specific star formation rate and the surface density of stars in each galaxy, and we're stepping through redshift bins for all of the galaxies in our simulation sample. And what you can sort of pick out is that galaxies tend to move to the right here, and then they move up. And because it's a little bit hard to see exactly what's going on in this movie, I'll show you some snapshots. So this one at redshift 4, it's quite clear that we have a relatively large sample of compact star-forming galaxies. These are comparable to the blue nuggets that Candle sees. Whereas at low redshift, you don't see these star-forming compact galaxies anymore, but rather you see a significant fraction of compact red galaxies. So one caveat, and this is something that Chris Moody was talking about the other day, is that, and Phil Hopkins was talking about it yesterday as well, is that most simulations suffer from too much early star formation. And you can see that here in the M star M halo relation. This is in blue our generation 1 simulation, so there's no radiative feedback. In red, our simulations with radiative feedback, and you see that M star M halo reduces once you add radiative feedback, but it's still a bit too high. And so what that means for this analysis is, if you look here, this is at redshift 6, we already have a lot of blue nuggets at redshift 6, and that's because of this very early on star formation. And if feedback was implemented in such a way that it could suppress very high Z star formation, this blue nugget formation would probably happen at a later redshift. So when I was showing you all those points as they moved in SSFR sigma space, it's very hard to pick out what any individual galaxy is doing. So I'm pointing out here 3 individual cases. And this is, again, a time sequence where over here you start out at high redshift, and here you end up at low redshift. And it seems like there's 2 different evolutionary paths here. So the first, which are the black and green simulations, seem to become very compact at high specific star formation rates and then slowly quench, whereas this red galaxy right here never really becomes very compact except for one time step. It instead becomes gradually quenched while remaining diffuse. So we want to know what's causing this very compact phase. And obviously, it's a dissipative process. And because these are AMR simulations, it's not trivial to trace what the gas is doing. In the sense that, you know, when we have a star particle, we don't know exactly where the gas that formed that star came from. So we have to use other tracers.
Is this for individual clumps or entire galaxy?
This is for an entire galaxy.
So you have, when you calculate the x-axis sigma, you calculate the entire smoothing.
This is for R effective.
R effective.
Yeah. OK, so as I was saying, it's, sorry, I thought you. It's not trivial to find what the gas is doing, so we're looking for ways of trying to figure out what is going on here during this dissipative phase. So I'll show you, for these 2 galaxies that become very compact, what they look like at around this redshift. This is for the black line. the galaxy shown in black. This is what the disk looks like at that time. And you can see that there's a ton of clumps in this galaxy, right? So this is very indicative of what Avishai was talking about earlier in the week, which is very unstable disks. And again, these disks drive in a lot of gas to the center of the galaxy. The same thing is true of the green galaxy, where again, this is the disk at that redshift where it gets to very high sigma at high specific star formation rate. And again, you see that there's this very clumpy disk phase. Now, another way of looking at it, which is more quantitative, is this. Let me unpack this slide a little bit. So what you're looking at here is the mass growth of the bulge in relation to its final bulge mass. And here you're looking at 3 different parameters. So mu3 is the fraction of mass added in a merger of 1:3 mass ratio, so a major merger. This is the same thing, but for minor mergers, so a merger of mass ratio anywhere between 1 to 10. And then this is n clumps, which is the number of clumps we find in the disk. And what you see for this particular galaxy is that it goes through a phase where the bulge is being built up through major mergers. Here you see that the bulge is being built up through minor merger, but then you go through this phase right here where there's no contribution from mergers, but still significant bulge growth, and this is occurring at the exact same time that the disk becomes very unstable, starts forming a lot of clumps, and presumably driving in a lot of gas. You see the same thing in this galaxy, but it's a more extreme example where mergers really play an insignificant or a relatively small part in building up the bulge mass, and the vast majority of bulge growth takes place during a period where there's absolutely no mergers, but a whole lot of instability. So I think what I'm hoping that I've convinced you is that the way that you make a very compact star-forming galaxy is to have a dissipative process, and at least part of that is being driven by inflow of gas through the disk. Now, what's triggering quenching? And let me just say that Joanna Wu's talk earlier on in the week covered this very nicely, so for more details you should look at her talk. But you can sort of think of 2 processes here. One is the sigma bulge quenching, where you have this strong gas inflow to the center of the galaxy, you have a starburst, and that starburst and the preceding supernova feedback really consumes all of the gas in the central regions on a fast time scale. The second process is halo quenching, which is a much slower process, and it's the long-term shutdown of gas due to virial shock heating. So what do the simulations show for this? This is the same 3 galaxies. I'm showing again the specific star formation rate, but now as a function of virial mass. And what you see here for the black line and the green line is you get this very rapid quenching. And this, if you correlate it with the surface density, both of these quick drops in specific star formation rate happen at very high sigma. So when sigma is greater than 10 to the 10. So this is pretty indicative of sigma quenching. Whereas for the red line, which never gets to high sigma, but rather undergoes a major merger here that adds a lot of mass to the galaxy, it looks as if this process is much more dominated by halo quenching. The black line, the galaxy shown in black, actually seems to be undergoing both sigma and halo quenching. So first, sigma quenching on a faster time scale, and then here it undergoes a major merger, and potentially there's more halo quenching here. So to summarize, I think one of the really interesting things we're finding is that at high redshift, something like 60% of the stars that are in the bulge formed there in situ. At low redshift, that fraction drops significantly, but it's still at least 30% of the stellar mass in bulges. And this will have implications for things like the ages of bulges and their metallicities. We find that there's a strong inflow of gas through the disk, and this brings in not only gas, but stars and clumps. And it looks like what's making bulges compact, though it's obvious that it must be a dissipative process, is not only wet mergers, but also VDI. And lastly, it looks as if both bulge and halo quenching is taking place in these simulations. Thanks.
All right, we have time for questions. James.
So on the plot where you had cell mass statistics versus starvation rates, it seemed to be kind of a tractor to like in the line. Like there was a fairly early inform. There was that spike, you know, all of it. There's a real spike at right at the time at the end.
That's right.
Yeah, well, do you know what that is?
So this right here.
Yeah.
So actually, because some of the galaxies have very fine time resolution, and I've put them all on this plot. This is actually the track of one galaxy that's becoming very quenched very quickly.
Okay, other questions?
You're all convinced. And sorry, I should have said, although it was written here, that as Joel pointed out, Lauren Porter has done some work on this with semi-analytic models.
Any evidence for rejuvenation?
I'm sorry, any evidence for?
Rejuvenation. So that means that the red nuggets will come back to the blue nuggets.
No, the gas consumption is pretty total, right? So there's not a lot of gas left to come back to the blue stage, at least in these simulations. Yeah, the gas consumption is very efficient. So you just don't have fuel left over.
Other questions? All right, well, chair's prerogative, I'll ask a question, which is, in your inflows, you mentioned that there's an inflow of gas and an inflow of stars.
Mm-hmm.
Can you say a little bit more about how much of each is coming in? Are you getting more inflow of, so does the fraction of mass flowing in match the gas fraction? Does the gas fraction of the inflow match the gas fraction of the galaxy, or is it higher or lower than the gas fraction of the disk? In other words, is the inflow preferentially gas, preferentially stars, or a fair mix of both?
So I haven't looked at that exactly, but you can see that at least, speaking in relative terms, there's a significant fraction of stars that are flowing into the center of the galaxy, right? So all of these green histograms are showing you the stars that were formed in the disk and then flowed into the bulge, right? So that's just to say that it happens.
Sure, it's smaller than the in situ. I'm just
That's
wondering,
right.
Yeah, so I'm wondering if the in situ is representing mostly gas that flowed in and then formed stars, or was it stuff that just fell directly from the IGM onto the bulge?
Right, so we don't know because we can't trace it, but it certainly looks like there's more gas flowing in than stars at each given snapshot.
Okay, yes.
So the giant gas clumps that you form in your really compact red galaxies, does the clump form in the disk like rotationally and then just get sucked in through like viscous drag or whatever like that, or does it form in a flow that's already coming in? Like, at what point do I see the clump? Does it as it's rotating, or does it start whole gas clump physically flowing?
So you see them in the disk, and they, on the time scale about 250 million years, they get dragged in towards the center.
So they start rotating and then it's just okay.
And we don't see very much clump disruption in these simulations.
All right, no further questions. Let's thank Adi again, and go to the next speaker come up.